So, hello everyone. Today I'd like to talk about decoding methods. So, decoding methods for language generation specifically. So, yeah, I will start with why I find decoding methods interesting and how I got into the details. And I will also touch upon the common decoding methods and some challenges they induce. And also I will pivot to typical decoding, which is a new method introduced recently. And also I will talk about some information basics. Finally, I will conclude with some takeaways. Yeah, so without further ado, first how I got into like those decoding methods. I'm not sure if you can see it. So when I was qualitatively evaluating those models I've trained. So this is not such a big model. It's a pre-trained model, like 1.2 billion. And we're asking it to explain the image in detail. And I found that, whatever like decoding methods I was using, maybe Spin search decoding or sampling decoding, whenever the text gets longer, it always gets into, a repetitive loop, right? You can see, the airplane is small, airplane with, white propeller, etc., etc. And this really got me into the nitty-gritty details of like, implementation and so on. And it turns out that I was not alone because, in the famous paper, this is the first version, not big two, they mentioned that, during their bootstrapping datasets, when they're bootstrapping datasets, they use this called captioner to generate synthetic captions. And they mentioned explicitly that, a nucleus sampling, which is one version of decoding methods I will talk about later, that really produces, diverse set of captions, which turns out to be quite important for training the language model. And I will talk about what diverse means and what surprise means. And also prior work has shown that, language models tend to have this like degeneration. For example, the foreground repetition for language models is 40%, and for humans like us is like 1%. Yeah, so let's talk about like sequence model. And in sequence modeling, we have three components, right? We have the model itself, it can be GRU, LSTM, transformers. It can be, and then the second component is the learning process, right? We can have maximum likelihood or maximum a posteriori, or then, which is the key topic of this talk, which is about inference and the decoding methods. So the goal of this like learning process or the modeling process is to first to estimate the probability distribution of the sequence, like from 1 to t, given the context. For example, we want given the context we get as there in German, then we want to predict the sequence how are you doing or how are you in English. Then during the decoding, what we do is that we have the decoding methods, the calligraphic F, and then it takes the probability distribution we learned, parameterized by theta, and then we want to draw from the probability distribution given the context after t times that t. And there are several, common methods in decoding, and the first one the first category comes with many names. For example, truncated or incomplete or maximization-based decoding methods. And the first one is the top K decoding. So what top K decoding does is that given a distribution, next token distribution, say we have the bundle of tokens, and in this case we pick the top 5 tokens, and because they are most probable, and we only want to continue with those tokens. But you might wonder why then this should be reasonable, right? Because we want to have the most probable sequences. Why do we need other ones. This is because, for example, if our distribution is not that picky, it's like quite uniformly because we only are given one there, right? And think about, for example, story generation, and this can go in any direction, right? But in this case, we're not quite sure which token to pick, and if you only truncate here, then the story would be always about dog or a nice guy. Yeah, that's why we also have a top P decoding where we have a target distribution. So here the hyperparameter is P, and we collect tokens from top to down, high probability to low probability until we match the probability target. This is, you can think of it as an adaptive way of top K decoding. And another set of category, maybe I should have mentioned this first, is like the simplest one. This is called stochastic one, or also called ancestral sampling. So basically, we have the next token distribution, and the simplest thing we can do is to just sample directly from the categorical distribution, and to get the next token randomly. And this can be combined, so for example, with some temperature scaling, where we put the scaling factor below the probability to make the distribution more peaky or less peaky. And then we have the new one, so-called typical decoding. I will talk about that a bit later. Also, we can combine a bunch of those methods that we've described above. And actually, in Ajax, we can do most of them, and we can combine them in any combination. But this decoding method really, induces lots of challenges, and why it can be a problem. It can be a problem is because we have the learned probability distribution in blue, right? But when we combine, when it's combined with the decoding algorithm, it actually produces a new distribution. Right, so the decoding algorithm can really induce a new distribution that diverges from the original one that we learned. And in this case, we can have non-overlapping paths, meaning that some sequences from the original distribution we learned will never be generated. And some of them that we never learned can be generated from the decoding method. And this can be problematic, and this causes several symptoms. The first one is repetition, as we've shown before. And then the second one is called the inconsistency. So a consistent model, if you like, produces always terminating sequence. And as I've tricked around, I find that if you don't set the maximum, well, if you set the maximum sequence length to a large number, it can really keep spitting out words non-stopping. This is because for the incomplete decoding methods we've talked about, the end of sequence tokens can really be truncated out because it's not very likely compared to other tokens. And another, the last problem is so-called logical contradiction. So in this case, let's give an example of GPT-2 completion. So I just say basketball is awesome, but I really dislike what. And in this case, if we use greedy decoding, we pick basketball, and this can really cause a logic contradiction.
Can you speak a bit more about the LMs are consistent of it? I guess what you're saying is like they would actually self-terminate. Like that's the context that you brought up. But like, how is that true? Why is that true?
Yes. So I skimmed through the paper. They have a formal proof, but basically the main idea is that the language models never put a non-zero probability mass on infinite sequences. So that's whole of their proof in idea. So if the sequence is infinite, then the probability will, ideally, is symptomatically converge to 0.
Okay, yeah. Okay, that seems true, but that just says like they will eventually produce an EOS by chance.
Yes, I guess that's
It's like an infinite contour.
Yeah, sure.
Yes, but yeah, eventually they will. Yeah, basically they say that the US token is always within the probability distribution the model learned. But if we have a decoding algorithm coupled with the model, then the EOS token can be eliminated from that distribution.
Okay, but that's not necessarily then a statement that the kind of repetition that you showed before is a result of incomplete decoding, right? Because for all we know, like, yes, maybe the probability to produce EOS after that sentence is like 0.01, right? And then it's still true that even if the decoding is perfect, right, it would eventually terminate. Just take a very long time of saying the same. I'm just trying to understand the scale.
Yeah, that's a good question. I think yeah, there are indeed like difference in the sense that this is a problem of truncation, and this problem is about repeating like high likelihood words.
Yeah.
Yeah. So yeah, I agree. Yeah, it's not.
And the number 3 is a decoding symptom?
I think so. So these 3 categories were summarized from prior work, and I think like the third one is a bit whimsical compared to.
I think so.
Yeah, because it's kind of a a side effect from repetition or like other decoding.
Yeah. Also, if you have like a Python as your language model, they would have just called a lot.
Yeah. Yeah, I agree. Yeah. That's a good.
Sorry, maybe I missed it as a question, but repetition, like why is it a symptom of the decoding?
Yeah, so this is the whole distribution of model learning, and this is the induced distribution of the decoding algorithm. And this part could be a very high probability, a subset of the vocabulary, and it turns out, well, there's no theoretical proof, but empirically, if you stay within this high probability words, and and when you guess, in later iteration, it will get into an infinite loop, and it will loop through those high probability words, and one induce another, and go on, like infinite. And this causes a kind of repetition. So it's like high probability words induces another high probability word, and they get back to the previous one, and this forms a loop. That's my understanding. But I don't think there is a theoretical proof why they really got into this problem.
But that could happen at P of theta also in the original.
Yeah, I think it can also happen here, but I think this is more problematic. In those high probability tokens.
P of theta is grid in that case? Not just like the model basically? Or?
Yeah, this is the blue distribution is what the model learned.
Oh, I see, okay.
The whole.
Yeah, so it could happen.
It could happen, yeah. So what typical decoding is trying to solve is to solve the problem of having dull and repetitive text, and for the downside of the stochastic methods, generating nonsensical or nonsense text because of the stochastic nature. And the objective here is really to mitigate the problem of repetition. So they are targeting the problem of repetition, and to generate like more interesting or human-like text. And we'll define what human-like means in their paper, and what's interesting means in this context. And before we dive into the technical details, I need to point out some assumptions those authors make. And the first category is from the psychological point of view. So in psychology, I think this paper is quite psychological. They talk a lot about how human produce words. They say that me as a human is selecting words to convey a certain message. So for example, I'm currently talking, I'm not sampling from the English dictionary with the most probable words, but I'm trying to convey a certain message to you guys, and in the most effective way. Secondly, so I'm not choosing those high probability words, but I'm choosing the word that really conveys the most important information. And so I'm not blindly following the distribution. And another hypothesis is from the linguistic point of view. So in linguistics, there is a theory called uniform information density. So basically, it's a mouthful, but basically it says that we don't like surprises. We tend to spread the information and the content throughout the whole sentence instead of making surprises. Yeah, maybe we do, but we don't do it very constantly, right? That would be very inefficient because surprises are hard to process. And yeah, and so for example, in this case, my boss confirmed that we were absolutely crazy. Right? This is an example sentence, and it's totally fine to remove that, right? Because it still makes sense. But if we remove that, we really, put we to the stage because it's now serving both the context and the starter of the word to give a more informed point of view. So this figure shows on the y-axis is the information density in bits, and then we have the sequences. So my boss confirmed. If we remove that, so this is the token that, then the information density at we will peak because it serves both the context and the onset of a new sentence. Yeah, so this is from a pretty old some information theory basics. So first is the information density or the information content. I always like to call it surprise density because it's the log 2 of 1 over the probability of a random variable. And yeah, log 2 here is because we are talking about information. So this is really the inverse of the probability, right? So if I'm saying, well, forever, and then the next time I say, well, you wouldn't be surprised because it's almost 100%, right? And so the more probable maybe is the more, less interesting. And this is one of the reasons why the prior work points out that, beam search text is kind of boring because it stays always on the safe side. It's always on high probability word, and the orange curve is what we humans do. So we sometimes have big high probability words like we, and sometimes we give surprises to low probability. And yes, so another thing I'd like to introduce is the entropy or Shannon entropy. It's not the one we use in physics. So it's basically the expected information density or the expected surprise. And then what we have is the entropy, so-called entropy rate or conditional entropy rate, is basically a generalization of the Shannon entropy. So what it does is that, first the authors assume like human language based on prior work is stationary and ergodic. Basically, it means that the stochastic process can be summarized by one single sample, one single sufficiently long sample. And we can get like very accurate statistics of this stochastic process. And then what really measures is the joint entropy, the average joint entropy, and it's a generalization because when the entropy rate, the process is IID, they are basically the same constants. And it's measuring how much new information is generated per token on average. So the expected surprise for each token. And then I think one of the theories that's typically heavily used in this paper is called the typicality. So typicality is basically saying that the average information content should not be far from the expected one and should be smaller than some epsilon. And so this set of tokens is called a typical set. It forms the typical set, and it says that it's a subset that hosts almost all the probability mass, but is not extremely probable. It's neither very probable nor very rare. For example, in this case, we're not at the tau. See here, oops. And it's basically like in the middle. It's not the most probable part, but it's like the typical ones we choose.
So here probability is per token or per sequence?
Let me check. Yeah, that's a good question. So in this case, we are talking about the whole stochastic process. In this case, this would be the whole bin or the whole string. Yeah.
Yeah, it also says probability.
Oh yeah, yeah. Okay. So the proposed method is called the typical sampling because it introduces a concept called so-called the locally typical set. So let me break it down. So basically, it's a conditional typical set because it's conditioning on the local context. So in this case, for example, what we're having here is the expected information density, so the expected surprise. And then here is for every step T, we're conditioning on the content and produces the token at this time step. And what we want is that we want the distance between the two. We want to minimize the distance between the two. And the tokens of this minimization objective is from a truncated set. The truncated set is a bunch of tokens that we collected to until we reach a probability mass tau. And this is quite similar to say top P sampling. Yes, so this is quite similar to the P in top P sampling. So for example, we have the word distribution here, and say the expected information density is like the red line. And what we want to do is that we have tau, the objective is 60%. And then we pick tokens. We say red is, well, maybe fox is the closest to the line. We pick that one. The red is the second closest. And then we have about 0.6%. The next one will be dog, but dog will not fit in the set because we have met our target. Then we will choose this and the subset to do our decoding. So this is like another objective similar to top P. Instead of P, we choose like more sophisticated.
H here is your entropy, it's your channel entropy or circuit typicality?
Yeah, H here is the expected information content. So we're trying to find the one that's on the y-axis is the expected, the information density of each token, and we are matching the information density of each token to the expected one. So we're saying that we don't want surprises, we want to find the closest one to the expected information rate.
How do you compute H then?
H is computed at every time step. So given the context, we compute the L, we compute the Y, so the previous context.
Why they call that H? Because that's the channel entropy is H. Usually.
Yeah. That's the convention. They use it as the convention.
Okay, but it's not like the channel entropy. It's like it's computed differently.
Yeah, it's the so-called entropy rate. So it's a generalized.
I see. Okay,
so it's like conditioned on the context.
Oh, yeah. Okay, because it's on.
It's a stochastic.
I see. Okay, thanks.
So they still can generate New York, for example. I live in New York because then York would have a very high probability, but H would also be very high, right? And then it's the token York is still in very close vicinity of our red line. Is that sort of the intuition?
condition that York would have a pretty low probability after you like the H also.
So if I say I live in New and now it's about to produce a token York, then York would have a very high probability, right?
Oh, I thought you meant entropy. Yes.
Yeah, it is very high probability. And then like so then our H would be also low. No,
But
it
then
must be high, right?
I think the other words would be sufficiently.
Yeah, the other like everything else is low. And then York is very high. I'm wondering how we can still pick the token York and the conditional.
But even if it's high, if the other words are sufficiently low,
Yeah.
it would still be closer.
Yeah.
Yeah.
Okay, so that's
Yeah, I think, yeah, that's a good question. I think in the paper, they also mentioned that one of the reasons why their methods still can generate those high probability tokens is because it really depends on the expected information density of that sentence. So if like York is close to the information density and that context window, then it will be generated. So I think they are trying to argue that in this case we're selecting tokens based on the expected surprise instead of the probability alone. Yeah, so one key observation they mentioned is this deviant epsilon. So epsilon is like the difference between this term and this term. And they said that, the human-like text, by human-like, they mean from like, human generated text. They said, what they measured is that, the difference is very picky for all the corpuses they've measured, and they all peaked at around 0, meaning that those two terms are very close. So that's one of the arguments they mentioned that why we should always, the objective makes sense because as humans, we try to match unconsciously our tokens or the words with the expected information content within the speaking window. But what they didn't explain is that why the shape and or what picky means in this case. For example, we have a very long tail, or like we have this high probability math, asymmetric math on the left side. But yeah, it's like they are in the paper like, hey, this is observation. So quantitatively, they want to argue that although the quantitative result they want to show is that although they are trying to minimize the repetition, they are still quite comparable in terms of those automatic metrics with other typical methods, for example, temperature, sampling, nucleus, top K, etc. In this case, they are using GPT-2 as the language model, base model. They plug in their decoding methods there, and the tau threshold is for story generation 0.2, abstract summarization is 0.95, which kind of surprising because this difference is huge. And so the perplexity, for example, here, G means fine-tuned model, I means independent, meaning that's not fine-tuned. And one thing I like to draw your attention to is that the evaluation matrix is not in the traditional sense because they are comparing with the reference. The reference is the crowd worker they hired on Amazon Mechanical Turk. So they're comparing the best one is the closest to that matrix. It's not the lower, the better. So in this case, the typical sampling is the closest. So in the brackets, there are differences. And in this case, yeah, it's not typical sampling, but in general, the performance comparable. It's not great, I have to say, but it's comparable, while dramatically reducing the repetition in the text.
Do they compare it against other, for example, like a beam search where they try to cap, let's say the sequence length is n, so 1/n is the probability of each token or something like that.
Yeah, that's a good point. So they didn't. I think in the appendix they have more comprehensive evaluation. I'm not sure there, but like in the main evaluation they didn't include, and I guess it's because nucleus is coming great the state of the art on most common tasks, and for beam search, especially for story generation, they wouldn't. Yeah, I think it's not a very strong baseline, but I'm guessing they didn't mention that. So I'd like to have some criticism for this work. Firstly, they didn't mention anything about consistency or contradiction, so that to our other three problems, and also it's kind of still disappointing because it's still within the realm of like truncated decoding algorithms. So I think they are trying to align their methods with existing ones so that people feel comfortable using it. But I think having a threshold is kind of a problem, and it would be interesting to see if we can really generalize this to remove it or to learn this threshold. And also again about this threshold, it's quite surprising they have this task dependent hyperparameter that can vary greatly from task to task, right? For top P or top K, I can just safely pick one and use probably for many tasks, and for this one I need to really pick the right one for it to work well. And quantitative valuation is quite worrying, so I really highly recommend looking at, for example, abstract summarization is quite bad compared to.
Actually, why do they need the threshold? I might have just totally missed this. Like, what's the point of the threshold? You just cut down the sample to the range around the expected entropy. Why don't you just like sample?
Yeah, I think that's a great question. So I think it's about limiting the computation cost, because the more words next token you choose, the more memory you need to give as to like the cumulative probability of this string.
I mean, you could still apply beam search actually, right? You just basically it's just a scoring method, right? Like it's not scoring by probability, it's scoring by expected surprise.
Yeah, that's true. Yeah, I think that's a good point. Indeed, Sarah, if I understood correctly, you mean that instead of doing this truncation via this hyperparameter, we can just do a beam search directly with
in different space, yeah.
In that space at different.
It's just a metric. I'm just introducing like a scoring metric, right?
Exactly, yeah. But in that case, there will be another hyperparameter, which is the beam width.
Yes, that's true. But I wonder if that would be more stable than the threshold.
I see. So I think what they're trying to do, so I think like your point is totally valid in the sense that it's kind of approximating top K.
Yeah.
And they're trying to approximating top P.
Mm-hmm.
And top P is believed to be like the adaptive way of top K when like the distribution shape is not peaky or uniform and stuff like that. So, for example, when we're picking top K and the distribution is uniform, maybe we should widen our choices at that step. But that's a good point.
I agree with Peter. It's completely complementary, right? It's like an additional layer. You just transform your probability output space, and then you could apply all top P or top K or beam search or whatever other decoding algorithm you would like on the modified score.
I think that they should have shown some like results, because I don't think it's a difficult thing to.
Exactly.
It's just okay. Thanks. So this is the last. Slide. So if you have to remember something from this talk, so I'd like to have some key messages. One is that decoding methods really matter. They can also introduce several challenges during the inference process because they can cause some deviation in terms of distribution, predictive distribution. And the typical decoding I just introduced is a new way of looking at it. It's not perfect, but I think it's a new interesting perspective. Yeah, that concludes. Thank you.
Thanks.
Yes, thanks. Questions? I also have some backup slides.